Okay, I will start my today's general club presentation. The title is Out of Distribution Detection. More specifically, today we're gonna talking about the likelihood-based approach. So before start talking about the papers, we're gonna talking about the short summary on the previous presentation. To understand the out of distribution, we have to talking about the in distribution and the out of distribution dataset. This definition is coming from that the in distribution dataset means that the class dataset which the samples are used in the training procedure, and out of distribution means that not included in the training procedure. So target of OoD detection is that we have the model trained from the in distribution data set, and we wanna find that how we classify the regression of the in distribution data set, and how we detect the out of distribution data set. So the target is that we wanna find the out of distribution data sample from the training models. Core idea is that if the test sample is input, then the output of the models is different between the in distribution and out of distribution dataset. So this is the common example of by using the MNIST web demo. MNIST is the 0 to 9, the number dataset. 뭐라 해야 되지? MNIST dataset is organized from the numbers from 0 to 9. So if we input the 7, if we drawing the 7, that the output node, the 7th node output has the higher values in the output of the model. But in the case, in the normal case, we just drawing the human face, but the output of that node is in this case the third node is has the maximum value from the output vectors, and also this one is the 0 has the large number of the large values of in the output vectors. So in these two cases, the model has model could misclassify the input data set even the sample is coming from the out data set, out of the distribution data set. In either case, to find the outlier samples from the model output, the output vector has to be like this. All values, not some of the node has the major values within the vector outputs. So by comparing these kind of vectors between the in distribution dataset, we could find the outlier samples. 국문으로 잠깐 서머리를 할게요. 그러니까 지금 아웃라이어가 들어갔을 때 미스클래시피케이션 된 샘플인데, 지금 아웃풋 벡터가 하나의 노드가 지금 메이저 밸류를 갖는 잘못된 아웃풋을 내주고 있고요. 이게 아무런 조치를 취하지 않았을 경우에 일반적으로 이렇게 나오는데, 이렇게 되면 우리가 아웃라이어 샘플인 거를 모를 수밖에 없으니까 아이디어란 케이스는 이렇게 유니폼 밸류로 나올 경우에 이게 아웃라이어다 라고 우리가 판별할 수 있고, 따라서 OOD의 목적은 이제 아웃풋 밸류를 이렇게 유니폼하게 만드는 게 하나의 목적이라고 보시면 되겠습니다. So this one, so we could talk that the OOD detection has the meaning that we have the training model used from the in distribution dataset, and we have to classify the in distribution data sample exactly, and we also detect the outlier samples from the training model. So approaches could be categorized as these three approaches. First, confidence score based approach. with and the second training procedure based approach, and third one today we're gonna talking about the likelihood based approach. So actually this first one, the confidence score based approach, we talked about it in the previous presentation, and now there is a short summary. So this approach is the confidence score, which could be defined from the output vector of the training model, which we already talking about this one. This one is the confidence score. So the target is if the test sample is input, there exists some model output or exist, and we have to we could compare the output vector of the samples between the in distribution and the output outlier data set. So by comparing that, we could find the outlier samples from the training model. So there are three models that exist. So there is some technique to magnify the difference between the in output vector of the in distribution and also output vector of the outlier distribution. These are the pre-processing, and also there is some in this paper, third paper, talking about the Mahalanobis distance, which is not using the Euclidean distance. By calculating the Mahalanobis distance between the distributions, we could find the more exact outlier samples. This one is the confidence score based approach. And second one is the training procedure. Actually, the previous one, the loss function in a training procedure is the same with the previous one, but in this case, they proposed some additional loss function for considering about the outliers. So these papers, by using the some proportion of the outliers data set in training procedure and make the loss function, and by doing that we could do the more exact OoD detections. And third one, likelihood based approach for OoD detection, which we're gonna talking about today's presentation. So these two papers are talking about the likelihood of the distribution. So in deep learning area, to training the likelihood of the distribution of the data set, we commonly use the generative models, and by calculating the likelihood from the generative model output, we gonna compare this blue one is the training data set, and this black one and red one is the outlier samples. By comparing this likelihood between the training model, we also could do the OoD detections. So now we're gonna talking about the likelihood approach. And before that, if you guys have any questions of the previous summary, please tell me right now. 잠깐 공문으로 서머리를 하면은 세 가지 방법이 있는데요. 컨피던스 스코어는 저번 프레젠테이션에 이야기를 했고, 트레이닝 프로시듀어, 그 다음에 오늘은 이제 라이클리후드 베이스드 어프로치를 할 건데, 컨피던스 스코어는 이제 그냥 학습된 모델의 아웃풋을 이용을 해서 이제 그 인 디스트리뷰션과 아웃 디스트리뷰션의 차이를 계산을 한 방법이고요. 트레이닝 프로시듀어는 이제 아웃라이어의 일부 샘플을 로스 펑션을 이용을 해서 트레이닝 과정에 이용을 함으로써 그 아웃라이어도 찾을 수 있게 만드는 방법이고, 이거는 이제 보통 제너레이티브 모델에서 나오는 그 생성되는 X에 대한 라이클리후드를 계산을 해서 그 라이클리후드를 비교를 했을 때 OOD를 할 수 있다라는 어프로치입니다. 그래서 이제 라이클리후드 어프로치 발표를 시작을 할 건데, 혹시 질문 있으시면 말씀해 주시겠어요? Now we start the presentation for the likelihood. Where is actually this paper first talking about how we compare the likelihood in a deep neural network. On these papers, the input data set is the oil transmission. There is some data set or exist, and they estimate how the oils are, we lose the oil during the transmission. 그러니까 데이터셋이 지금 오일을 전송을 할 때 송유관에서 센서를 달아서 측정된 매저 값을 가지고 얼마나 오일이 유출되는지를 측정을 하는 그런 데이터셋이 있는데요. The main point is the white one is the common procedure for estimation the how we lose the oil from during the transmission, and by adding the likelihood, by learning the probabilistic density model for true distribution of the training data, which means that likelihood values also trained in the neural network, and when comparing that, this x point is the in distribution data set, likelihood values of the from the in distribution data set, and make the other testing the likelihood values of the outlier samples, and we could definitely found that the value distribution of the likelihood values is different with the in distribution data set. So in this paper, just propose the comparing the likelihood values, which means that if the likelihood values are less than the training data set sample, then it is the outliers. 그러니까 이제 likelihood value가 distribution 명확하게 다르다라는 걸 처음 보여줬고요. 그래서 in distribution dataset의 likelihood보다 더 적을 경우, 그러면은 지나치게 낮은 likelihood를 가질 경우 이거는 outlier다라고 첫 번째 이야기를 한 베이직 페이퍼라고 보시면 되겠습니다. So the core is that the likelihood of the outlier samples should be smaller than the training in the in distribution dataset samples, but in recent days, this problem are reported. That this blue one, also in this figure, the blue one is the in distribution dataset. We could show that the likelihood values are similar with the training and the test dataset within the in distribution dataset. But the problem is that this black one is smaller than the blue one, but in red one is the larger than the blue one. Also same problems are on here. The red one and this 뭐라 해야 되냐? This ImageNet 32 dataset also less than the blue one. It is okay, but in the green one case, it has the larger value than the blue one. So the problem is that we in the previous page we told that likelihood should be smaller than the training dataset, but the likelihood values is different from as the dataset are changed. 그러니까 이제 데이터셋이 바뀌면서 likelihood value가 더 적게 적어야 된다라는 가정이 어떤 거는 더 적고 어떤 거는 더 크고 라는 문제가 발생을 해버린 거죠. So this because of the so in recently papers talking about these issues, and the problem is that the likelihood derived from the generative model failed to distinguish between the training dataset and the OoD dataset. So these kind of many papers are talking about this problem, and this the board one we are talking about these two papers. Solution, but these papers within these papers, the solution idea is coming from this one. How we let 이거 왜 이렇게 적어놨지? The common solution is the how we calculate the likelihood from between the training dataset and the OoD dataset, not just the threshold one. So the first paper is the WAIC papers. This paper title is here, and the approach is simple. These WAIC values are already exist in the estimation method area, and these values are defined from that asymptotical correct estimation method of the gap between the training set and the test set expectations. So in the probabilistic model, if we had to access the sample from the Bayesian posterior model, we could calculate the correct version of the correct 그러니까 잠깐 공문을 할게요. 확률 모델에서 모델이 여러 개 있을 때 그거에 대한 익스펙테이션 값을 취해줌으로써 이제 저희가 모델을 딥러닝에서 모델을 할 때 로컬 글로벌 미니멈을 찾는 게 아니라 로컬 미니멈을 찾는다라는 이야기를 많이 하잖아요. 그러다 보니 트레이닝 모델이 10개가 있으면은 10개에 대한 라이클리후드 밸류가 모두가 100에서 나오는 게 아니라 어떤 거는 뭐 10, 어떤 거는 뭐 1000 이런 식으로 모델마다 찾는 로컬 미니멈이 다를 수밖에 없다는 이야기거든요. 그 경우에 이 WAIC라는 익스펙테이션 모델을 통해서 이 데이터셋이 갖는 정확한 모델 그 라이클리후드 값을 계산을 할 수가 있다라는 내용을 갖고 있습니다. 이게 이제 에스티메이션 메소드에 원래 있었고요. So the WAIC, the correct estimation method in estimation area already exists. So they apply these WAIC values to the generative models. So we already said that there is to estimate these WAIC values, there is we should get many kind of models. So in this paper, they apply the generative ensembles, which means that make the likelihood estimation method. WGAN is used in this paper. They make that for the 10 models and doing the expectation for calculate the correct likelihood values. So they propose the 잠시만요. So their proposed method we could say that concretely an ensemble of the generative model that computed an exact or the approximate likelihood are used to estimate the WAIC values. 잠깐 서머리를 하자면은 이제 WAIC라는 모델이 여러 개 있을 때 정확한 라이클리후드를 재는 익스펙테이션 방법이 원래 있었고요. 그거를 위해서 이제 WGAN 보통 라이클리후드를 계산을 하려면 저희는 GAN 모델을 쓰니까 WGAN을 여기 적용을 해서 모델을 여러 가지 여기서는 10개를 만들었을 거예요. 10개를 만들고 그 라이클리후드에 대한 expectation을 취한 겁니다. So by calculating these WAIC values, these smaller figures are the previous one, and this the bigger figures is the WAIC values of the generative ensemble model, and we found that the blue one is on here, and the other three outlier dataset, the values from this outlier dataset shows the smaller value than the training dataset. So we could say that the likelihood problems are solved, which we talked in the previous paper, previous page. Clearly, SBHN and the ImageNet, and also these values. This left one is the not applying the WAIC values, and this right one is the after applying the WAIC values, and the measurement is the AUROC curve. We could definitely show that by applying this approach, the ROC curve, performance of the ROC curve shows the clearly improved. So this one is the method from the paper 1. Now we're going to talking about the paper 2. In this research team also measured that the same problem in the previous paper. The blue one is the training one, and the other data set shows which one is shows the smaller one, and some of the data set shows the higher values in the likelihood. So they make the hypothesis that the generative model based on the likelihood values of the generative model are influenced by the input complexity, which means that when the authors checking the dataset from on here, the right one, they also showed that the image shows the black image or the just right the handwrite image of the some object, which means that the input complexity is less input complexity or exist in the upper part, and also checking this similar one or the previous one, they also show that the more complex than the training data set shows the less data set. 그러니까 지금 말이 좀 꼬였는데요. 잠깐 서머리를 하자면은 이 문제에 있어서 라이클로드 데이터셋에 대해서 데이터셋을 체크를 해봤는데 높은 밸류를 보이는 이런 부분에 있는 데이터셋은 블랙 이미지나 아니면은 이런 그냥 간단한 글씨 오브젝트를 그린 것만 같은 좀 더 복잡하지 않은 데이터셋이었다라는 거죠. 그 다음에 이런 비슷한 놈이나 가장 작은 놈, 노이즈가 가장 컴플렉시티가 높을 거고 이런 밸류들을 보면은 훨씬 더 복잡한 데이터셋이었다라는 거죠. 그래서 이거를 이제 휴리스틱하게 체크를 하고 나서 그 히포테시스를 채우고 만들고 그거를 이제 증명을 하기 위해서 다음 실험으로 넘어갑니다. So to make concrete hypothesis on the previous page, they artificially make the image based on the input complexity, which means that this one is just noisy image, not a first they make the uniform random noisy image with the same size of the previous input, same size with the training data set, and after that average pooling is applied and upsampling, nearest neighborhood upsampling method are applied. By doing that, the pooling factors is different from 1 to 32, and this left one shows just one color, the gray colors are exist in the input image. 그러니까 지금 가장 복잡한 이미지를 랜덤 노이즈로 만들고 그거를 에버리지 풀링을 했다가 리얼리스트 네이버루드를 이제 할 경우에 근처에 이제 32를 기준으로 하나의 밸류 값을 만들고 그 값을 다시 이제 같은 값으로 업샘플링을 했기 때문에 인풋 컴플렉시티가 명확하게 줄어든다라는 거죠. So by checking the likelihood values of this artificial data set, we also check the result that likelihood values going to the grower as the input complexity going to less. So to make some value from the for measuring the input complexity, the author make the question. Okay, then how we measure the input complexity in the image? They got the idea from the lossless compression method. PNG, JPEG, this kind of compression method are categorized as the lossless compression, which means that there is no data loss in the image. So they make this kind of values. If the images is complexity of the image is the smaller value, then lossless output of the lossless compression should be the shorter. And if the image is complex, then output of this compression output vectors also going to the larger value than the which is smaller one. 그러니까 lossless compression output 벡터를 기준으로 이미지가 간단할수록 이제 로스레스 컴프레션의 아웃풋 벡터는 더 짧은 벡터를 가질 거고요. 이미지가 복잡할수록 이제 정보를 잃지 않기 위해서는 컴프레션 아웃풋 벡터가 길 수밖에 없겠죠. 그거를 기준으로 지금 이제 인풋 컴플렉시티를 나타내는 밸류를 추가로 매저를 겁니다. So by define the complex value some measurement values to considering about the input complexity and compare the relationship between the input complexity and the likelihood values, definitely we could show that these two values has the negative relationship. So from this the negative relationship, the author defined the out of distribution scores, which means that in the previous score we just use the likelihood, but we minus the input complexity from that values. So this scoring Also, author talking about how we use this score in the practice values, but in this paper, they just use this score value directly as a score for find out of distribution detection. So this one is the result. The SVH, the last one is the not using the not considering about the input complexity, and the right one, this S values, is the after considering about the likelihood value. So from the result, we definitely show that this kind of data set shows the uh, problem in the previous 그러니까 이 데이터셋들이 이전 결과에서 문제가 보여줬던 데이터셋들인데요. This dataset, we could show that also this one is the ROC curve. The value ROC values definitely highly improved after considering about the input complexity. Also, this kind of data set this data set shows the similar values with the training data set. Because of the reason, ROC values is similar with the 1.5, but this data set also shows the improvements from the data set. 그러니까 잠깐 구문으로 넘어갈게요. 그러니까 이 데이터셋들이 오른쪽에 있던 이 로우 데이터셋들이어서 기존의 방법으로는 ROC 커브 밸류가 0에 가까웠죠. 거의 못 찾는다는 문제였는데 이 밸류들이 인풋 컴플렉시티를 적용을 함으로써 ROC 커브가 확 증가가 된 걸 확인할 수가 있고요. 이 데이터셋들은 이 비슷한 라이클리후드 값들을 보여줬던 데이터셋들인데 이 값들 역시 이 전 방법에서는 비슷한 밸류였으니까 거의 잘 못 찾았던 거를 1에 가깝게 확 임프루브니스를 보여준 걸 확인할 수가 있습니다. Also in the case of test dataset, which means the in-distribution dataset, the ROC measured at the 1.5, which means that we could find the in-distribution dataset from the likelihood. 그래서 이제 in-distribution dataset인 테스트 데이터셋을 이용을 했을 때는 0.5로 이제 잘 랜덤하게 찾는 것과 비슷한 결과를 보여줄 수가 있는 거죠. Comparing with this ROC values between the classification based, which we call the confidence score based approach, and also compare with the likelihood based approach. This is the highlighted one is the paper presented on this today's presentation, and the value show that the WAIC, in case of WAIC, the CIPAR, when the case of CIPAR 10 training dataset, the OoD detection ratio going to almost 100%, and also the second paper approach. This highlighted one shows the good ROC curve result within these two dataset. 그래서 지금 두 데이터셋을 이제 접근 방법에 대해서 비교를 한 건데요. 명확하게 likelihood based approach가 더 좋다라고는 이야기를 하고 있지는 않고요. 근데 classification based, 그러니까 confidence score based approach와 랑 다른 특징 중 하나가 likelihood based approach를 할 경우에 그 트레이닝 데이터셋이 바뀌어도 이 OoD 디텍션 레이시오가 크게 달라지지 않는다라는 이야기를 이 페이퍼에서는 마지막으로 결과를 보여주고 있습니다. So this is the end of today's presentation, and to do the OoD detection, we are talking about the three categories. To talking about the possible approaches, and when we thinking about the common features of these three approaches, we could know that if the test sample is inputted, then when we comparing with the output vectors of the model within the in distribution and the output outlier distribution, by comparing to that, we could find the out of distribution dataset. 그러니까 잠깐 이제 마지막을 공문으로 한 번만 더 정리를 하자면은 OoD 디텍션을 하기 위해서 뭐 세 가지 방법을 저희가 이야기를 했는데요. 저번 프레젠테이션이랑 이번 프레젠테이션이랑 일단 컴피던스 스코어 같은 경우는 뭐 명확하게 클래시피케이션 문제지만 뭐 제너레이티브 라이클리후드 문제 같은 경우는 뭐 리그레션 문제에도 충분히 적용될 수 있는 어프로치로 보이고요. 이 방법들의 커먼 피처는 이제 저희가 인 디스트리뷰션 데이터셋이랑 아웃라이어 디스트리뷰션 데이터셋이랑 둘 간의 아웃풋 벡터를 비교를 함으로써 어떻게 비교를 할지는 각각의 어프로치에 따라서 정해지고요. 이 두 개를 비교를 함으로써 우리는 찾을 수가 있다, 충분히 찾을 수가 있다라는 결론을 내릴 수가 있습니다. So this is end of today's presentation, and if you have any questions, please tell me. 그래서 지금 제 문제니까 저는 이제 클래시피케이션을 다루는 건데 뭐 나중에 딥러닝 모델을 사용을 할 생각이 있으시다면은 그리고 그 중에서 내가 고르지 않은 뭐 데이터에 대한 워닝을 주고 싶다, 디텍션 모델을 만들고 싶다라고 할 경우에 오늘 프레젠테이션에 사용했던 방법들이 뭐 충분히 사용될 수 있을 걸로 판단이 되고요. 질문 있으시면 해주실래요?